England 0, Belgium 1 after 58 minutes. So I suspect no one other than me is interested. But, OK. It's been pointed out to me that there is an error in this slide. This dy by dt should be a y in here, not an x. And the same is true on the following page. So I will correct that, and thank you very much for pointing it out. OK, what I was saying at the end, just before we broke, was that we can use these partition function expressions here. And I finished one slide early because I should have gone on to this. These are the equations we've shown before, which give us the expressions for the internal energy, the entropy, and the heat capacity. And from these, we can get any thermodynamic quantities that we need. But basically, you've got the partition functions dependent upon masses, structures, and vibrational frequencies, and electronic energy levels, and you can then pop these into these expressions here to get thermodynamic quantities. OK, where do we get these data from? So here's I don't know, does anybody use the NIST webbook? Yeah, OK. So the NIST webbook is a good source of data. So this is for methane. So this is the enthalpy of formation of methane at two different temperatures. No, sorry, two different determinations. And also the vibrational frequencies for it. It's just let's have a quick look at it. Oops. So here's the website, and you can just go in. Let's click formula, so we can go and look at, say, the methyl radical there, and look for gas phase data, and we could look for the infrared spectrum, or we could look for vibrational and electronic energy levels, so there's the methyl radical. So look for the gas phase thermochemistry data, and there it is. That's what I copied out. The problem with it is that it hasn't been desperately well updated. So you can see from those 1998, 1996. So that doesn't give you a lot of confidence because things have changed since those days. So that's something of a problem with the NIST site. But one good place to look is, which you can get to from the NIST site, is this computational chemistry comparison and benchmark database. Do you use that? This really is good. And so it covers compounds with atoms with atomic number less than 18, which is argon, although some heavier species are there as well, and 6 or fewer heavy atoms. By heavy atoms, they mean things like carbon rather than hydrogen, and quite a lot of data in it. So just let's have a look at that. So here's the data on this CCCBDB database for, these are experimental data for the methyl radical. So again, for the methyl radical, but, oops. Sorry about this. Okay, I won't touch anything. And notice there that the enthalpy of formation comes from 2005, and it comes from RUS. So this is Rusich. And we'll be talking about Rusich later on. Rusich is at Argonne National Labs, and he is really the king of thermodynamic databases. So I strongly recommend this particular database because it's pretty up to date. And it contains not only thermodynamic data, but a lot of spectroscopic data as well. So these are data from the NIST web book, and this is to emphasize some of the problems. So these are the calculated data that are given with this density functional theory analysis. And you can see that this low frequency vibration is really significantly lower than the experimental value here. Sorry, this is from CCCDBBD, whatever it is. But this is looking at the calculated values and comparing them with experiment. Here's methane, again, calculated. This is very low level. This is a Hartree-Fock calculation. And for the stable molecules, it's doing a bit better. But even so, these frequencies are quite a long way away from the experimental values. So you need to be careful with where you're getting the data from. Now, if you take something like methane, then its enthalpy of formation has been determined using, say, combustion calorimetry. So something like methane is relatively easy to deal with. But a radical like methyl, you can't do an experiment of that sort. You can't do calorimetry on a methyl radical. It's too short-lived. So how do we determine the enthalpies of formation of radicals? So approach not feasible for radicals, and an IUPAC evaluation of thermodynamic data for radicals can be found in Rusich. So if you go to JPhysChem reference data, it's quite an old paper, 2005, but it gives you a discussion of how this evaluation has been done and how the thermodynamics have been determined. And so an example is methyl, and you can use kinetics, photoionization spectroscopy, or electronic structure calculations. And the recommended value by IUPAC is that, with an uncertainty of 0.3 kilojoules per mole. Pretty accurate. But how have those been determined? What you can do is you can do the kinetics of a forward reaction and a reverse reaction. So measure KT for this for a radical plus HI, so say CH3 plus HI, or tertiary butyl plus HI, any alkyl radical that you want. And this was done particularly by the group of David Gutman. And so these are the experimental data. So this is the pseudo first order rate constant as a function of hi. Getting a good rate constant out, you can see the precision of the data. And these are those rate constants as a function of temperature for different species, for methyl going up to tertiary butyl. And the interesting thing about these reactions is that they have negative activation energies. The rate constant goes down as the temperature goes up. And for a long time, there was a big disagreement in the thermodynamic literature because people just didn't believe these negative temperature dependencies. But they can be rationalized theoretically along the lines that we've discussed. There's a very strong van der Waals interaction between the tertiary butyl radical and HI. HI is very, very polarizable and interacts very strongly with the tertiary butyl radical and even with methyl. And so we have a complex form before the inner transition state, and that can give rise to this negative temperature dependence. So there's the forward rate constant. You can combine that with the reverse rate constant, and that gives you an equilibrium constant. Okay? And then you can determine the reaction by what are called second and third law methods. So you can say that minus RT log K is equal to delta G standard, which is equal to minus delta H standard minus T delta S standard. And what you can do is, if you express the temperature dependence of these things in some form or other, you can then plot the logarithm of the equilibrium constant versus temperature, and from the slope you can get delta H. So d log K by d1 over T is equal to minus delta H over R, provided this doesn't depend upon temperature. But you can then modify that expression so you allow for the dependencies here. Alternatively, what you can do is you can calculate the entropy using statistical mechanics and then determine this enthalpy change directly from it. So these are what are called the second and third law methods. But so you're getting this quantity from the forward and the reverse rate constants, and then from that you can get the enthalpy of reaction, and then from that the enthalpy of formation. Yeah, I should really put R's in there to show that's the enthalpy of reaction. So for example, this is TC4H9 plus HI going to C4H10 plus I reversibly. So that gives you, so we can find the enthalpy of formation of this, and of this, and from that we can calculate the enthalpy of formation of the T-butyl radical. Alternatively, what you can do is you can look at the equilibration directly. So this is a pulse photolysis experiment looking at H plus C2H4 going to C2H5. And if you're high enough in temperature, then the C2H5 can dissociate back to the reactants. There's also a loss process in which the H diffuses out of the region you're looking at. And so from this, you get a bi-exponential decay. You can analyze it using the methods we discussed on Monday. And so there's the decay at room temperature, which is pretty exponential. Here's the decay at high temperatures, which is bi-exponential. And so from this, you can get the forward and the reverse rate constants. And from that, you can get the equilibrium constant and treat it in exactly the same way as we discussed in the previous slide. This is the photoionization spectrum of CH3. And so what you can do is you can photoionize the methyl radical, producing CH3 plus the electron. That's reaction 1. And here's that process there, and there's the threshold for the reaction coming down. So you need to analyze this curve, and the threshold for the reaction, threshold energy for the reaction, corresponds to the energy of this photon here, 126.5 nanometers. You can then do the same sort of thing with methane, and going up to enough energy so you produce CH3 plus H plus an electron. And so this takes, sorry about the difference in units, this takes something like 14.35 electron volts. And so if you take R2 minus R1, you then get the energy for CH4 falling apart to form CH3 plus H, and then from the enthalpies of formation of CH4 and H, you can get that for the CH3 radical. And this is a very accurate way of doing it. And if you go to this paper, which is quite old but is very, very useful, you find tabulations of what are called bond enthalpy changes. So bond enthalpy changes, so DH298 for RH is basically the dissociation energy for this bond here. And that's going to correspond to the enthalpy of formation of R plus the enthalpy of formation of H minus the enthalpy of formation of RH. And so once again, you can get the enthalpy of formation of R from that bond dissociation energy. Sorry? How do you get CH3 in the first place? Yeah, so the question is, how do you get CH3 in the first place going back here? So how do you get CH3 in the first place? This will be done in a discharge. So you're bombarding methane with electrons and then looking at the CH3 downstream of there. So you have to have some way of dissociating a precursor to produce the CH3 itself. Okay? The bond energy change or dissociation energy at 0K is this. So 0K, this actually corresponds to the enthalpy change at 0K as well. And bond energies can be converted to bond enthalpy changes using the relation U is equal to H plus PV is equal to H plus RT. So that for RH going to R plus H, you get delta U is equal to delta H plus RT. And at 0K, they're exactly the same. And so there's an extensive data set in there which does contain some useful data. But over the last few years, there's been this development of thermodynamic databases, what are called active thermochemical databases. And a particularly important one is based at Argonne National Labs, and it's called ATCT, Active Thermochemical Tables, and it's been led by Branko Rusic. And it's discussed in this paper here. And over the last few years, they've made tremendous advances with this and now have a website which is very, very easy to use and very useful to use that we'll have a look at in a minute. And NEAT, we'll also refer to later on, is based in Budapest. And this man, Attila Sazar, is a leading theoretician, and NEAT is based on theoretical calculations. So active thermochemical tables, there's the website, and it covers currently, as of May 2016, so this has probably been enhanced, 1199 species. So a lot of species are in there. And just let's have a look at the way, what it's based on. So supposing what we do is we look at this relatively simple reaction system here, carbon, oxygen, and so we can go from CO2 to carbon plus O2 by dissociation. We can go from C plus O2 to CO plus a half O2, and we can go from CO plus a half O2 to CO2. And we've got two species there, CO and CO2, and we've got three determinations. So there's a redundancy, if you like, but in addition, that larger number of determinations than the numbers of quantities you need helps you improve the accuracy. And in particular, it allows you to throw out data that may not be correct. And so this is a much more extensive one. So this is just part of hydrogen, oxygen. So you can go from water liquid to water vapor. You can then ionize water, forming OH plus H plus electron. You can dissociate the water to form OH plus H and finish up with H there, OH there, and H there. And you can then ionize the OH and get an energy for that process as well. And so on, all the way around here. And so this is a small subsection of the current core argon thermochemical network. This is taken from quite a time ago. And the full network contains many, many more than this. And this is, if you like, an illustration of what's going on. So what we've got down here are entries for water, for hydrogen, and for oxygen in this big matrix. And here's a reaction in which we go from water, in which we take hydrogen plus half oxygen and form water. So we've got water is being produced, and then H2 and a half O2 are being used up. And then there are other reactions in here as well. So the reactions are listed down here, reactions 7, 8, and 9. So different entries, different enthalpies of reaction, and also different uncertainties for those reactions. And so these uncertainties are important. And then what you do is you do an optimization of all of those enthalpies of formation that are present in that matrix. This is a demonstration of one of the key developments that came out of this. I remember people from Argonne National Labs talking about this problem in the 1990s. And this is a paper that was eventually published in 2001. And what they found was that these original determinations, which came from several years ago, don't have the dates of them, but they do come from quite some time ago, must be an error. And this was an experiment done by Rusic, which showed very clearly that the true thermodynamics was lower than the values which were determined up here. And it turned out these two determinations up here were spectroscopic determinations, but wrong assumptions had been made in the interpretation of the experimental data, which gave a consistent overestimation of the enthalpy of formation of OH. And Rusic's data demonstrated very clearly that that was incorrect. And then this was a calculation that was done around about the year 2000, much significantly more uncertain than one would be able to do it now. But nevertheless, this agreed very well with Rusic's experimental values. And so this led to a redetermination of OH. And those particular measurements and determinations would go into this overall thermodynamic database and allow the improvement in the calculated enthalpies of, improvement in the enthalpies of formation, tabulated enthalpies of formation for other species as well. So here's an example, CH3. This is taken from ATCT. This is the 95% uncertainty limits for methyl. These are in kilojoules per mole, and you can see how incredibly accurately that methyl radical enthalpy of formation has now been determined. And these are 95% uncertainty limits, so it's better than 1/10 of a kilojoule per mole. And it's quite interesting to go into this database and look at where the data have come from. So what they have is a method which allows them to determine what they call the provenance of the estimate. So they can see which measurements, so each of the measurements that they've got, that they've put into this big matrix, have got an uncertainty associated with them, and they contribute in different ways to the determination of this enthalpy of formation. And saying that there are many, many contributors to this determination of the enthalpy of formation of methyl, and the top 20 contributors account only for 70% of the provenance. There are a total of 99 contributors that account for 90% of the provenance. So that shows how many determinations are being incorporated into ATCT and allowing these very accurate determinations of enthalpies of formation. So ATCT is a really good place to go to get very accurate thermodynamic data. So there's the link. And here's ethyl, again, really quite accurately determined. Now not as good as the methyl, but it's better than better than 1/3 of a kilojoule per mole. And just let's have a look at this this website here. So what we can do is let's put down species name, let's put down C2H5. Let's find it. Oh, I managed not to put down the right. It's not being very kind to me here. Sorry? Oh, yeah. It would be better if I put it in there, wouldn't it? Yeah. Wow. It does improve if you put it in the right column, doesn't it? Okay, so here's ethyl, and here are the top contributors to the enthalpy of formation. And you can see that the top one is contributing only 4%, and that's a measurement by Rusic using this photoionization methodology. The third entry at 2.6% is a kinetics measurement, ethyl plus HBr going to C2H6 plus Br, and that is actually several determinations at this same temperature of 530 K. So you can see once again that a lot of data have been put into these active thermochemical tables, and they're giving rise to these really very accurate determinations. Let's try another one. So let's try CH2. Okay, so here what we've got is methylene. And methylene, as we said, can exist as a triplet and a singlet. And those are the enthalpies of formation. And once again, they're really very, very accurately determined to the order of something like 1/10 of a kilojoule per mole. And those give us the most accurate assessment we can have of the difference in energy between this singlet and triplet. Let's look at the triplet. And look at the provenance of the enthalpy of formation of the triplet. And these, if you look into them, are all theoretical determinations. These are all electronic structure calculations that have been used to determine so accurately this energy of the triplet. There was the difference in energy between the singlet and the triplet was not well known for many, many years. And there were experimental determinations of it, but strong disagreements between them. It was then determined really quite accurately by experiment, but now those measurements are being completely superseded by these very high accuracy theoretical determinations. So that's really very impressive data. And this is an interesting application because the reaction between CH plus H2 is important in interstellar media. And interstellar media have a temperature of not very much, a few degrees Kelvin. And so you need very, very accurate determinations of rate constants and of enthalpies of reaction in order to, of activation energies, sorry, in order to be able to determine rate constants accurately. And so this was a determination of the enthalpy of this particular reaction here, which was used to determine quite accurately the rate constant for this direction, triplet CH2 plus H, from very accurate measurements of CH plus H2. But you needed really very accurate determinations of the uncertainty in that determination. And at the bottom, what I've done, so the enthalpy of reaction is known to something like 0.08 kcal per mole or 0.35 kilojoules per mole. And determining the uncertainty at 1,000 K for combustion applications and at 10 K for applications in interstellar chemistry based solely on the enthalpy change, you need to do this sort of calculation here. And at 10 K for interstellar media, even an uncertainty of this sort introduces a significant uncertainty in the overall rate constant that you're calculating for that reverse reaction. And at the bottom, note the heavy reliance on theory for these determinations in ATCT. Okay, we're going to say something about theory determinations in a minute, but does anybody have any questions? Everybody's fairly happy. Okay, so this next slide is linked to ATCT, but provides a different source. Whoops. So these are ab initio calculations. So ab initio computations and active thermochemical tables hand in hand, heats of formation for core combustion species. And this is by the argon group. And they're high-level, very high-level ab initio electronic structure calculations for 348 carbon, nitrogen, oxygen, and H-containing species. And essentially, they're all the core combustion species with 34 or fewer electrons. So that's a bit restrictive if you're interested in dodecane, but this covers an awful lot of species, especially radical species, for combustion. And they explore the accuracy of the theoretical predictions by looking at the magnitudes of the various corrections they've incorporated, comparisons with other high-level calculations, and through comparison with ATCT values. They did these calculations, it must have been about 3 or 4 years ago, and took some time to publish them. I was fortunate to get the Excel spreadsheet from them that contained all the data, and it has been incredibly useful to use. And now having them in the paper, in paper form, really is very, very useful. So inclusion of these theoretical results into ATCT is expected to significantly improve the thermochemical knowledge base for less well-studied species. So some quite bizarre radicals that are significant in combustion, and also some stable species that haven't been well-studied experimentally have been included in this. There's another set of calculations that comes from this group in Budapest. And this is the abstract. Simple, fast, weighted, linear least squares refinement protocol and code is presented for inverting the information contained in a network of quantum chemically computed 0K reaction enthalpies. So again, it's really very similar to the approach used in ATCT. These are for really quite small species, but nevertheless, they're very accurate. And they're contained in this database here, which respect TH, which is spectroscopy, thermodynamics, and reaction kinetics is what it means. And it contains thermochemical data calculated by that neat method, high accuracy thermochemical data for water. This is because of the need to understand the spectroscopy of water and how much water is going to be in any particular circumstances you're dealing with. And then they also mirror Burkhart's thermochemistry database, which we'll come to in a minute. So again, let's have a quick look at this. So this is going into this database, and you can see that there are kinetic data, spectroscopy data, and also thermochemistry data. Let's go into the thermochemistry data. You do actually have to get a username for this, but so it gives you a link to Burkhart's website. Which, as we'll see, provides thermochemical species in polynomial form. And this is the basis of the NASA representation. And you can get the files here. But if we go back there is a really rather nice application here. So what we can do is let's put in a species, let's put in, say, C2H6, search, show data. And what this gives you is plots of the thermochemical data. And so this is for ethane, and you can see that the temperature dependence of the heat capacity of ethane because of this change in the population of the various vibrational states. So the heat capacity is changing really quite a lot over a temperature range from 500 to 6,000 K. One of the nice things is that you can go into here and you can actually get the heat capacity at any specific temperature. So there's the heat capacity at 2300 K, which is 163.285. I suspect not quite that amount of accuracy is appropriate, but you can get it under any of these circumstances around here. So it's really, really quite useful. And then if you scroll down, you also have the enthalpy of formation and the entropy. So you can get the parameters that have been used to calculate those by going to Burkhart's site, or it's really quite nice and useful to go to this site and just be able to look them up at a specific temperature. You might have to interpolate, but okay. Incorporation of thermodynamic data into rate calculations. So this is that Burkhardt site that I was telling you about. And this provides data in NASA polynomial forms with 7 parameters that are related to necessary thermodynamic functions of state. So how many of you have used NASA polynomials? Okay, so quite a few of you. It's the great thing about NASA polynomials is they give you the data directly. They should be kept up to date. But it's always quite useful to use the ATCT data and go and see just how well they've been updated. Make sure that for some species, for species you're interested in, the NASA polynomials are giving you good results. Okay, so what there is a set of polynomials, A1 to A7, and the heat capacity, the enthalpy, and the entropy are represented in terms of these polynomials. And it's linked to ATCT, and it's used in ChemKin. So these are the data for methyl, so you can see these parameters. And the first 7 entries are for 1,000 to 6,000 K, and the second set are for 200 to 1,000 K. So you can cover the whole range from 200 to 600 K using these parameterizations here for those 3 thermodynamic quantities. And it may be the dinner tonight, but there's something to do. If you could pass those back, please. Thanks. Thanks. You're a bit more spread out than you have been for some reason. I can't think why. Thanks. Thank you. Okay, so what this gives you are the Does anybody not have one? Is anybody prepared to admit they don't have one? So what this gives you are the polynomials A1 to A5 between 1,000 and 3,000 K for nitrogen. And asks you to calculate the heat capacity over the temperature range 1,000 to 3,000 K. Then calculate the vibrational contribution to the heat capacity, given that the translational and rotational contributions are 3R over 2 and R respectively, using statistical mechanics. Well, from that and also then using statistical mechanics. So you're taking the NASA polynomials, you're subtracting 3R over 2 plus R, allowing for Cp is equal to Cv plus R, and then comparing those results with what you would get from statistical mechanics. And so there's an expression for the heat capacity from statistical mechanics and the frequency of vibration of nitrogen. Comment on the differences. And on the back, there's a reminder about where those things have come from in StatMech. Okay, so we'll have a look at that tomorrow. The results are quite interesting, and it will be interesting to know if you understand if you get that far, why there is a difference between them. Okay, a couple of issues here. So this is another approach. This comes from chemical engineering in Cambridge, a big data framework to validate the thermodynamic data for chemical species. Validating data for standard enthalpy of formation for 920 gas phase species retrieved from the NIST chemistry web book. And we know there are some problems with that. And they use error-cancelling balanced reactions to calculate the distribution of possible values of the standard entropy. Now, what they mean by isodesmic reactions are reactions in which there are the same number of atoms on one side of the reaction as on the other. And it turns out that under these circumstances, they can minimize the energy of reaction, the enthalpy of reaction, and that allows them to calculate these things more rapidly. So they're using NIST, but then they're doing calculations. They're DFT calculations, and the method automates the identification and exclusion of inconsistent data. So what they do is they look at all the possible determinations using these using a variety of methods, eliminate outliers, and then use those in a rather similar way to ATCT. And it exploits the knowledge of the structural similarities between species and the consistency of the data to identify which species introduce the most error and recommend what future experimental calculations should be considered. So it's an interesting paper and indicates one of the ways forward to improving enthalpies of formation for a variety of species. And then one of the other things that is done is to use what's called group properties. Have you come across the use of group properties in thermodynamics? Anyone? Yes. Okay, so this is a newer way of doing it, using a variety of approaches and characterizing the group interaction within a molecule with an exponential decay function from group to group distances. So if you've got, say, butane, then in principle you can determine the properties of the butane molecule by looking at the properties of CH3, CH2, CH2, and CH3. Once of a day, one would simply put in the independent values for those quantities. And a man called Sidney Benson was very central to the development of this group additivity approach. What this is doing is looking at the interactions between these species as well. So interactions come from a variety of sources, and this is using an exponential decreasing decay function from group to group distances defined as the number of bonds between the different groups. So this is allowing for interaction, but saying the interactions from an energy point of view is going to decrease as you go along the molecule. And it's more, they claim that it's more accurate than conventional group additivity using the same training sets. So that's by he et al. From a couple of years ago, and worth looking at. Okay, well, that's all we're going to do about thermodynamics. So we're going to go on to evaluation of rate data next, and then on to reaction mechanisms. And we'll probably get on to reaction mechanisms by the end of today, and then finish it off tomorrow morning. But let's break there and come back in quarter an hour.